Welcome to the Pit Stop, your monthly tune-up with refining experts. I'm Doug Aswell, your host. Today our program is going to be about move into the fast lane with isotherming and hydroprocessing technology. We're going to be talking about something I found to be quite exciting, this technology called isotherming. And our experts, Samantha Presley and Sandeep Pollitt, which are CleanTech's isotherming gurus, are going to be talking about this very efficient, highly effective technology. Well, with all of that said, let's get going. On to our next pit stop. So we're back, and today we're going to be talking about isotherming and this interesting process that CleanTech has. And I have our guest with us, Samantha Presley and Sandeep Pollitt. And Sandeep and Sam, I think you're okay with me calling you Sam, I believe.
Yeah, no problem.
Cool. All right. So I know this isotherming technology is fantastic. There's a video out on YouTube, and I think we're going to try to have that link available for everyone to be able to view that. The facts that it talks about all of these advantages of this technology is pretty amazing. That it saves space in a plant, that it's energy efficient, that it utilizes the catalyst better than what conventional technology has in it. And it's used all over the world. We're definitely going to talk about it in depth. But before we get going with that, I want an opportunity for both of you to have a chance to kind of introduce yourselves and let our viewers know who you are. Some of them may have met you, but for those that haven't, get to know you a little bit as well. So, Sam, why don't you start and
Sure.
we'll finish up with Sandeep.
Yeah, well, thanks for having us on today. So I'm Samantha Presley, as Doug said. I have been with DuPont since 2010. I have a degree in chemical engineering and came into DuPont as a chemical engineer working on the technical side of proposal opportunities. And then for the last 3 years, I've had this role as the global licensing manager. So I get to work with Sandeep and lots of other awesome folks in the US and around the globe.
Sure.
And we have a really awesome job just going out and working with potential new customers, trying to license the isotherming technology that we have. So,
Cool.
um,
So you went kind of from a sales support side to a technical side at some point in your career as
yeah, I
well.
started out on the technical side only and then started
Oh,
to get out and meet face to face with customers a lot more, and then have transitioned now into both the technical and commercial role. So, our
awesome.
team works with potential new customers on developing opportunities. Sometimes it's straightforward opportunity if they know, I want to build a 30,000 barrel a day hydrotreater. Sometimes they come to us with an existing unit and
Mm-hmm.
they want to make it, run more efficiently or have longer catalyst cycle length and want to know what the technology can do for them. So those are really exciting opportunities to work on kind of developing hand in hand with the customer what the technology can do for them. So our team, interacts with the customer all the way through contract negotiation and sale.
Cool. All right. So you get to work with Sandeep. So
I
Sandeep,
do.
give us a chance to get to know you a little bit as well.
So I graduated in 1986 from Worcester Polytechnic Institute. It's a school in Massachusetts for engineering.
Mm-hmm.
And I joined DuPont in 2012 after working for a number of engineering companies. I also worked for a mobile technology company and also ExxonMobil in hydrocracking. So my background in hydroprocessing is quite strong, as well as in process engineering. So
Fantastic.
um, I think, what excites me about this technology is hydroprocessing hasn't really changed much and in its history, and isotherming is just something so unique and so fantastic that it just really attracted me. Like, how can I put it? Like electric cars are these way. This is kind of how I see isothermic. It's like, wow, this is the future. And so
Right.
I've been very much in this and committed for, I don't know, this is my 8th or 9th year or something like that. And
Fantastic.
I'm very excited about it.
Sandeep loves his job. I
Yeah.
will say that. He always says, I have the greatest job in the world.
Right, right. I
And let me just say one thing about Samantha. Like, actually, in our company here in Kansas City,
uh-huh.
everyone starts out as technical because we are very focused on technology and how to be the cutting edge.
Sure.
And so Samantha, even though now she has a broader role, she is very technical. So I expect she'll be answering most of these questions.
All right, very good. Very good. That's good to know that. When I was watching that video, I was thinking, man, I really wish I'd have gone into petrochemical because this sounds super exciting. I mean, you're offering something that a change to a technology that's like a reinvention of the wheel. That's a much better wheel at the same time, and it's like pretty astounding. I mean, one of the things that really caught me was the 50% reduction in operating expenditures. You know, the 50% OPEX on top of the footprint is smaller and a lot of other things, and we'll talk about a lot of that, I'm sure, as we go. But I could well imagine why folks like yourselves with a technical background in petrochemical would look at this and go, wow, this is a fantastic opportunity for our clients. So, what makes isotherming so attractive for refiners? What's the big deal about isotherming, and maybe a little bit of a background of what isotherming does for the refiners, just as to paint that full picture. What does the isotherming process do with that hydrocracking, hydroprocessing? What is it all about?
Sure, I can take that. So,
Sure.
as Sandeep said, traditional trickle bed hydroprocessing has been around, for a really long time. It's one of the oldest processes and widely used in multiple places throughout a refinery.
Mm-hmm.
So it's really well known and well understood by the refiners. Um, Isotherming is different in the sense that we're doing a lot of, we're doing the same reactions, the same chemistry,
Mm-hmm.
but we achieve it differently, and we achieve it, in a more cost-effective way, as you said, Doug.
Mm-hmm.
So you need to deliver hydrogen to the feed in order to have the chemical reactions take place.
Mm-hmm.
So in traditional trickle bed hydroprocessing, they do that with it's three phase. You have catalyst, you have liquid, and then you have hydrogen gas. We're doing two-phase process.
Mm-hmm.
We have the catalyst, and then we actually dissolve the hydrogen in the liquid. So utilizing hydrogen in the liquid instead of in a gas, we're able to deliver that solubilized in a recycle stream
Mm-hmm.
with a pump rather than with a really large recycle gas compressor machine.
Right.
For anyone that's been in a refinery and has seen one of those, they are, really large, costly, and take a lot of utilities to operate. So that right there is a huge savings, both on the capital side, the plot side, and the utility side. That's probably the most well-known benefit of the technology, to be honest, is the pump versus the compressor.
Mm-hmm.
But the benefits go way beyond that. So you hit on some of them, and I'm sure I'll miss some, Sandeep, so feel free to chime in. But the way that we handle heat management in the isotherming process is by directly transferring that heat from the reaction to the feed. So we don't need to supply as much heat to heat up the system.
Right.
And then not only that, a lot of the times there's excess heat left over after the reactions have taken place. So we can take a unit that is there really to comply with a regulation. Let's say, make ultra low sulfur diesel for you. And we'll do that, but we can also produce utilities for the refinery. We can produce medium pressure steam or low pressure steam, or help provide electricity to the refinery. So
Just for
not
some other
only do,
process elsewhere in the plant, just to make
yeah,
other
or turn around
operations
and
more
use
efficient.
that, use that steam or use that electricity to power part of the isotherming unit.
Wow.
So,
Okay.
a lot of the times these units are there to comply with the regulation, and we will do that, but we will also help them do it in a way that, can produce utilities for them, for example.
Wow.
Sandeep, would you like to add on to that at all?
So since we're mostly speaking about energy consumption, if you think any hydroprocessing unit has a very big recycle compressor. And what
Mm-hmm.
it does is it supplies a large amount of hydrogen well in excess to make sure that the unit or the reaction zone has enough hydrogen so that it can do the reaction and make the product you want.
To finish going to completion.
Yes, exactly.
Right.
So hydrogen is well in excess. And in isotherming, hydrogen is more controlled in the sense that we have a recycled liquid that's the carrier of hydrogen. And what we do is, based on how the feed changes, we inject hydrogen to resaturate the liquid and always keep that reaction zone in a very optimum efficient place. So we don't have so much waste. Sort of like if you look in a car, and you have a very large engine to provide you the power. And then let's say, okay, yeah, sure, I have this big engine and I can go, at slow speed, at high speed, different speeds, and I have always well enough power in excess. Whereas in isotherming, think of the engine being more efficient. Like when I need more power, I can provide that power. When I need less power, I provide less power.
Sure.
So like in China, for example, when we had several very large units, 50,000 barrels per day or more, come online, making ULSD, you see how much is the energy savings per year? It's in the millions of dollars.
Yeah, we have one
Wow.
customer that calculates, I believe, $10 million of energy savings a year.
Wow. And I'm assuming making better quality product out of the unit as well. I mean, I know that in the video it mentioned about the trickle-bed technology has problems occasionally with coking of some of the hydrocarbons, but the technology we use, being radically different, doesn't do that. So you actually end up with better, I would assume, cut points or better separation, better product quality out of the final product that you derive from the hydrocracking process.
So Doug, just keep in mind that we're trying to meet, our products are, say, diesel or kerosene. Right. So there's regulation as to what quality your product needs to be.
Sure. Yep.
So it's not really that we make a better ULSD than trickle-bed. It's just that we make it more efficiently.
Right.
And if you think of a refinery margin, it's not that much. So saving money on utilities is very important. Having an extended run length is helpful because you don't have to shut down the refinery to change the catalyst. Stability is important, operability is important. The main thing is, in a year, how reliably can you produce your product to meet market demand?
Absolutely.
Well, and on the topic of coking, Doug, so that mechanism will take place. It's part of hydroprocessing, whether it's with trickle bed or with isotherming.
So if you think about a trickle bed, what happens is that the heat of reaction is very large. Hydroprocessing is an exothermic reaction.
Right.
So what happens is that as you react, you produce heat, and that heat then leads to vaporization.
Right.
And what happens is that the temperature rises a lot, and then as the temperature rises, it increases the coking rate. So what happens in the trickle bed is you add quench, say you increase the temperature by 25 degrees, you quench it down, and then you react it again. This is how it works in a trickle bed. In isotherming, what we call is we have a heat sink with the liquid circulating. So there's a lot lower temperature rise because of the circulating liquid, and we don't have vaporization. So the catalyst itself stays in a very narrow range of temperature compared to a trickle bed. And because of that lower temperature, there's less coking. Also, if you think it's liquid full, we have a customer in the US that had a VGO hydrotreater, and basically they were getting about an 18-month catalyst life out of that unit. And they were having coking issues. And what we did is we put in an isotherming unit ahead of it. And what we saw is that the life of that unit became almost double, if not longer, because we could manage that exotherm so much better in isotherming. Most of the reaction was occurring in the isotherming reactor, which had a dampened temperature effect, as I had talked about. And the cycle length went from about less than 2 years to 4 years or longer from a catalyst activity standpoint.
Wow.
And so this is just, you can see if the aging rate in trickle bed was 2 to 3 degrees F per month. And then once we put in the isotherming reactor, the aging rate was about 1.5 degrees per month. And not only that, when we put in isotherming, we weren't making the same product. We were trying to get them from tier 2 gasoline to tier 3 gasoline. So because of that, it was running much harder. The hydrogen consumption was almost triple.
Oh, wow.
Okay, so if you can think, triple the hydrogen consumption, triple the heat release.
Oh, yeah.
So, it should burn up, right? But no, it did not.
Be coking all over the place, but it wasn't.
Exactly.
You're learning, Doug.
Yeah.
So I mean, typical cycle length is it really varies based on the application. Are you talking, kerosene, middle distillates, VGO, or mild hydrocracking? What's the pressure of the unit? So I'd say typical cycle length for us is substantially longer than trickle bed. So Sandeep gave a really good example for a VGO hydrotreater. We have a diesel hydrotreater that's currently in design right now. Again, it's an existing unit. So these are really good ones for us to know how was the customer operating before and how are they either operating or how are we forecasting that they'll operate after conversion to isotherming.
Right.
So this particular customer is getting about a year cycle length out of their unit. And after converting to the isotherming technology, we're projecting 2.5 to 3 years. But again, as Sandeep said, it's not on an apples to apples basis. Not only are they converting to our technology, they are, changing to a more difficult feedstock as well. So it's going to be more severe operating conditions.
Oh, yeah. That gets into another whole factor of this. I mean, is isotherming able to handle feedstocks that traditional hydrotreating can't handle? I mean, you just seemingly partly answered that they're able to use some feedstocks that it sounds like they wouldn't have been able to use before. So that's another piece of versatility of isotherming, it sounds like.
Yeah, so I mean, we see this a lot with revamps where a unit was maybe designed 10, 15 years ago for, more straight run feeds, and straight run feeds have, less aromatics, less heat release associated with them. And now they want to run cracked material. Maybe they want to run coker naphtha that has a lot of olefin in it, or, something else that just is a more difficult application leading to higher temperatures or higher hydrogen consumption, higher heat release. So because we have better heat management and, use of our catalyst with the isotherming technology, we're able to exceed, the previous limitation. Maybe that customer knows, well, I can only process 10% LCO in my unit currently. And if I go beyond that, my cycle length is toast. Well, isotherming may be able to take them to higher LCO amounts in their unit than they can currently. So we're processing a lot of the same feedstocks, but for an existing unit, we're often able to take on a larger percentage of that cracked material than currently is being processed in the unit.
A ton of things that can actually go through this isotherming process besides performing hydrocracking, which we've been talking about, hydrotreating. It can also perform hydrocracking and dewaxing and gas liquid conversion upgrade, and it sounds like a ton of different operations. And is that things that the conventional technology can't do or doesn't do quite as nifty, or is that totally new things that isotherming is capable of doing? That's another advantage of it. And the reason why I'm asking that is you mentioned the cracked feeds. Maybe think of some of these other unusual items that may go through the hydrotreating occasionally. So give me some fodder on that.
Yeah, so these applications are all applications that trickle bed could do as well. So it's just that we're doing it, in a more cost-effective manner.
Okay. And able to run longer and get longer cycle times. And that whole concept about being able to have longer cycle times, it's pretty easy to do the economics of that. I mean, if you're only having to take a shutdown every 3 to 4 years instead of every year, holy moly, that's a big difference real quick. So that is phenomenal. And you mentioned about cracked feeds and being able to handle that. Is that something that, yes, the conventional technology can handle? It's just that the ability of having better control of the temperature and less coking makes those crack feeds easier to deal with in isotherming, or is that a misunderstanding on my part?
Sandy,
I can take that. So what you have to remember is that a unit has to be designed for that type of feed in a trickle
Okay.
bed. So, if we design a unit for crack feed and conventional technology designs a unit for crack feed,
Mm-hmm.
they both have, we can design it so that it will be a 4-year cycle length. Our competitor can design it for a 4-year cycle length. The question always becomes in revamp situations where a unit has been designed by an original licensor for a less severe treat, and now they want to expand, or the refinery has become more complex and they put in a coker unit,
Mm-hmm.
to improve the overall efficiency and economy of the unit, and they have an existing unit. How are you going to improve that existing trickle bed unit, because it has its limitations? And I remember I told you that the recycle compressor is really what limits it. If it's designed for handling only, say, 100 scuffs per barrel, and now you're going to have 250, you get to a limit in that recycle compressor. In isotherming, what we can do is we can put in the recycle pump, and so we don't touch that loop, so that the trickle bed reactor, the recycle gas compressor won't be needed, because we're just putting in a pump and reusing the catalyst volume.
Gotcha. Okay. All right. I see. Are there any stories where a conventional hydrotreating unit's been replaced with isotherming and you're able to maybe almost double your complete capacity? Because it looks like a better utilization of footprint on the ground too. I mean, just from the video, I would assume that example it shows a traditional unit, and then our unit's like maybe 40% of the size, but yet I would assume able to handle at least, if not maybe more, of the original capacity of that conventional unit. I'm sure there's stories out there of that. So give me an idea of that if you have any.
I just want to mention that there are a lot of refiners worldwide that are not mega refiners. Okay, what I mean
Okay.
is they have small topping units
Sure.
that process 5,000, 10,000, 20,000 barrels per day.
Mm-hmm.
And what they're looking for is they want a very low cost solution. And because, they don't have footprint, they don't have the resources to do all the external offsite requirements. They just want a small unit that is going to give them ULSD, because the regulations say we need to do it. So we did this for a couple of transmix units here in the US.
Mm-hmm.
Basically, they are small operators. They buy feed from the pipeline wash, and what they want to do is they want to resell it for diesel. And so isotherming, in terms of the cost, it's so small compared to a trickle bed that needs a recycle compressor, or even if it's once through, it needs a high gas to oil ratio. And
Mm-hmm.
so it's more expensive. The utilities are more expensive. And the footprint, like you mentioned, is larger. If you think of a small refiner in, say, Indiana, they don't have space really to put in a unit. So they say, oh, okay, DuPont, I have this field in the back. Can you build me a unit over here? Or in
Mm-hmm.
Brazil, I went to this one refiner. They're like the oldest refiner in Brazil. And they showed me the plot, like, sir, can you fit your unit in here? In between these two units, between our FCC and our crude unit. That's all the space we have. And I said, yeah, we can fit that in right there. So
Wow.
space becomes very big concern in revamps, and in small refiners that, they'd be out of business if they can't make ULSD because regulations are coming.
Yeah.
Right. Right.
Yeah, and Doug, I guess, on your question about capacity increases that we can achieve with the isotherming technology and revamps, it's really application specific, because
Mm-hmm.
it doesn't just come down to throughput, it really comes down to hydrogen consumption as well, as Sandy was mentioning earlier. If a refiner is going to keep the same throughput but change out the feedstock such that the hydrogen consumption's double, they're going to run up against a limitation. So
Right.
just a couple of examples that I can think of off the top of my head. We're working on one diesel hydrotreater right now where the unit was operating around 150 cubic meters an hour. We are able to bring the unit back up to 205 cubic meters an hour. So it's about a 30% increase in capacity. And I'd say that, you know, getting a 25 to 30% capacity increase is pretty typical with what we can achieve, sometimes even higher than that, because again, not only are we increasing capacity, we're increasing capacity oftentimes with more challenging feedstocks that are going to take more hydrogen per barrel of feed. So we can't look at it on just a pure capacity basis.
And if by chance your plant doesn't have a bottleneck on hydrogen production, then that's perfect. If they do have a bottlenecking issue with hydrogen, they got to figure out how to overcome that to utilize that increased capacity, it sounds like. So that,
Yes.
So,
certainly
Doug, I have
that.
one point to add here.
Yeah, sure.
Is oftentimes, you know, a unit, they have the ability to increase capacity from a crude unit standpoint, but they're limited, they're bottlenecked by the hydrotreating unit. And so, you know, they always say, oh, how can we increase capacity? You know, and there's only so much, like I said, you can do with a conventional unit, because when a conventional unit has a bottleneck that's not fixable with minimum investment, that's when isotherming starts to look really pretty. Because if you think you have to modify the recycled gas compressor, or you have to modify the heater, these are things that can be cost prohibitive. Whereas with isotherming, you know, when we put that in, it doesn't impact their recycled gas loop. It doesn't impact the heater. Just remember, when we say convert a reactor to isotherming with the liquid recycle, we're recycling heat within the reaction zone. So the heater duty will actually go down, even though they're increasing capacity.
Yes.
Right.
So these are things that, you know, refiners are just really excited about. And again, you know, it's a matter of investment. How much investment can you make to revamp your unit versus building a grassroots unit?
Sure.
Grassroots unit is very expensive. So always, you know, think, okay, you know, I have a unit. Can I revamp this for 20 million versus spending 200 million toward a new unit? Yes. And that's where, you know, we have a very big advantage.
Yeah, and I think that, you know, that's a great point, Sandy. Now more than ever, with, you know, the pandemic world that we're all living in, most people aren't breaking out their checkbooks to spend, you know, millions and millions of dollars on huge capital projects. So you may be listening to this podcast like, well, you know, we don't need additional capacity out of our unit. Well, we can still provide value, even if you don't need additional capacity. What if you got double the cycle length that, you know, you are currently operating at? What is that additional uptime worth to your refinery? Or what if you're able to, you know, process more challenging feedstocks that currently you're selling at a pretty deep discount? And these are the really exciting projects that we get to work on, is when a customer comes to us and they want to do something more with their unit, and we can help them, like I said, kind of define what is that amount of investment that they can make that's, you know, minimal investment, but gives them maximum return on their existing assets.
Gotcha. Well, speaking of, you know, revamp, you know, they've already got catalyst that they use for this. I mean, is the catalyst that we use in our isotherming technology, is that our own catalyst, or can the client use their existing supplier of catalyst for that? I mean, give me a sense of what's going on with that as well.
That's a good question. So DuPont does sell catalyst. It is isotherming catalyst. It is, I would say it has a lot of the same properties that you see in conventional trickle-bed hydroprocessing. It is going to be, you know, potentially a nickel moly catalyst or a cobalt moly catalyst, trimetallic. Albemarle is our exclusive manufacturer of the catalyst. But DuPont does sell catalyst specific to the isotherming process. While the catalyst itself is similar to what you would see in trickle bed, our know-how really comes into how to design a catalyst load specific to the isotherming process, because the heat release happens differently. The temperature profile is going to look different. We're, you know, two-phase process instead of a three-phase process. So that's where, you know, the combination of our know-how on the technology side and Albemarle on the catalyst side is really great in what we're able to provide our customers. So
So I'm sure our catalyst has some advantages we could talk about, but if the client wants to use their existing feedstock or supplier for catalyst, we can design the isotherming unit to use their catalyst instead of ours, or whatever they want to do, it sounds like.
Yeah, so as a technology licensor, we're often asked to provide performance guarantees to a unit.
Sure.
So we do require that the customer purchase the first load of catalyst from DuPont in order to have those performance guarantees.
Sure.
But after that, just like any other unit, they're free to go out and bid, catalyst on the open market. But again, they're really only going to get that know-how of how to most effectively, load the catalyst in the isotherming unit by coming to DuPont and Albemarle.
Sure. Gotcha. So, all right. So we have a client who buys one of these units. What kind of support do we offer? I mean, do we send people for startup? Do we send folks or help? Yeah. Oh, really? Oh, awesome. So they get one of the experts in the field then, it sounds like.
No, we have a tech services team, which is quite experienced. Our subject matter expert is also very experienced. I would say we have in our tech service team more than 100 years of combined experience. So
wow,
we are not, just, what I say, a process technology supplier. We support our customers all the way from, doing pilot plant work with their feed and R&D to doing process engineering, to doing tech service and support, where we have the full package. And of course, we, being a new technology, we want to be involved in every phase of, from design to concept to startup. We have actually many of our units were built in China, and we have tech support engineers in China who support them. So support is key to making sure that the refinery is running well, our unit is running well, and we have monitoring of how the catalyst is performing. We provide advice, so it's quite important because if you think diesel, or if you have a hydrocracker or VG hydrocracker, these are essential units in the refinery's profitability. Right. So we want to support them every way we can.
Yep.
Yeah, that's one area that I think clean tech is really set apart from a lot of other process licensors is in our level of customer support. I mean, this goes not only for our isotherming technology, but our strat coagulation, the MECS technologies, our Velcro scrubbing technology. We really, we want to be partners with our customers, not just through, unit startup, sign the performance test and walk away.
And then walk away. Yep.
Yeah, we want to have, lifelong relationships with these operating units. So we'll do, site visits on a frequency. If it's our catalyst, we will monitor the activity and provide, reports like any other catalyst vendor would. We want to have, close relationships with our customers.
Right. Well, how long has this technology been around? I don't think I've asked that question. I mean, it sounds like an amazing new thing, but how long has this technology been around?
I mean, for the refining industry, it's still considered pretty new because, hydroprocessing has been around for so long.
Sure.
It was developed in the late 90s, early 2000s. The first unit was started up in 2003. And then DuPont actually acquired the technology in 2007. So it was previously developed and owned by a company called Process Dynamics, and then DuPont acquired it about 14 years ago.
Cool. Awesome.
So our longest operating unit, I guess, is coming up on 18 years here.
Wow. So it's not, last year was our first operating unit and it was 78,000 barrels a day.
We've had a total of 16 installations. So
wow,
we do have a fair number of references out there.
Good. Well, that's great to know. Well,
Doug, I just also want to mention that, even though that we've acquired the technology a number of years ago and have quite a lot of new innovations, I think, hydroprocessing isn't static. Our technology isn't static. We are constantly developing it. We learn from our customers. We make changes. Changes in the catalyst loading, changes in the design. Where I would say, if you think, okay, an iPhone, why do we need a new iPhone every year?
Right.
Well, it's same thing with, technology is, you never stand still. We keep improving to be competitive. And DuPont has spent millions and millions of dollars in improving this technology. And when we first had this, it was for 500 ppm diesel, then 50 ppm diesel, then 10 ppm diesel. So, as the product quality becomes more stringent, we've had to make changes. How do you make catalysts more efficient? We made changes. So there's a lot of work that goes into keeping a technology competitive. And DuPont, being a company, that's a strong technology-based company, they have invested a lot to make sure that our technology is the best it can be today.
Excellent. That's good to know. Well, hey, it has been wonderful having the two of you on with us today, both Sam and Sandeep. I know you have a lot of experience and have a lot of potential opportunity, it sounds like, for other clients to venture into this isotherming technology at some point. I'm sure it looks attractive to a lot of our client base. But it's been good to have you with us. And I want to mention to stick around for the question and answer session. It's coming up in just a few minutes. If you haven't asked a question yet, click on the link at the bottom to be able to submit one of those questions via the chat menu on the bottom. And don't be shy about it. Let's ask our experts while we have an opportunity if you have a burning question. And we'll also have their contact information available as well. So with that said, on to the question and answer session.
Sounds good.
And we're back in the question and answer portion of our program. And we're here with Sam and Sandeep. It's good to have you with us. And like I said in the intro and said a couple of times, this is a really cool technology. And I hope that our listeners enjoyed hearing about it, those that especially those that may not know a lot about it. But we've only got a few questions so far. So if you haven't submitted a question yet, go ahead and get that in right now. And certainly if you have a question later, Sam and Sandeep will be happy to answer those. We may have to do that offline, but that's no big deal. So let's get started with these questions. In fact, somebody just put one in. Let me ask this one first off. For large capacity units greater than 100 kbpsd, processing a mix of straight gas oils and cracked gas oils, what would you expect savings in catalyst volumes as compared to conventional DHT?
Okay, that's a good question.
That's a mouthful.
Yeah. So it said over 100,000 barrels a day processing. Yep. Can you repeat what the processing mixture of
straight gas oils and cracked gas oils? What is the expected savings in catalyst volumes as compared to conventional DHT?
Okay. So, I mean, to give an exact number, we would need to know, what is what's the crude source? What cracked material is it? Is it from a coker unit? Is it
probably
LCO?
Which catalyst you're using?
Yeah. I would say in general, we have a new configuration called inside loop, outside loop. And utilizing that configuration, we really are able to save on catalyst volume, especially with high hydrogen consumption applications. So I would say catalyst savings of upwards of 30% could be achieved compared to trickle bed.
Wow. Well, that's pretty significant. Yeah. So
I don't know if you want to agree or disagree with that.
So I can just quote our subject matter expert is that isotherming, when designed correctly, should result in 20 to 50% less catalyst requirement.
Wow.
But it's usually, very much application dependent. Right. For this particular application that this customer is asking about, I would say it probably will be around 20%.
Okay. All right. Next question. What is the operational reliability of isotherming compared to TBR mode for ULSD units?
Sandeep, do you want to take that one?
Sorry, guys. Can you repeat that question one more time?
Oh, sure. No problem. What is the operational reliability of isotherming compared to TBR mode for ULSD units?
Okay, reliability.
Mm-hmm.
So reliability is subject to the refiner, if he or she is able to operate the unit within the design constraints. Let's say we have two refiners who are just excellent refiners who know how to operate TBR or knows how to operate an isotherming unit.
Sure.
So how is our unit more reliable? Well, you have to remember that refiners, usually there are upsets that happen in a refinery. And so during that upset, there might be a temporary shutdown. And what happens in isotherming when you have a shutdown? Well, our catalyst, because of the way the reactor is configured, it's
Mm-hmm.
in a totally immersed in liquid. So what happens, and we've shown this, in a power failure or anything, what happens is that the temperature rises and it heats up the liquid and then it begins to cool.
Mm-hmm.
When you have, say, a power failure and the reactor remains liquid full. So, and then when we come back from the power failure, we don't observe any activity loss. Whereas in a trickle bed, if the same thing happens, because there's such a large amount of hydrogen in the reactor,
Mm-hmm.
temperature rises much more. You have to de-inventory, you have to depressure. So
Right.
that kind of an upset can cause activity loss. So in that sense, yes, it's much more safer. The catalyst is much more safer in an isotherming unit than in a trickle bed. So that helps your reliability.
Yeah, because it sounds like the liquid acts as a heat sink and prevents the catalyst from coking and that kind of thing to some extent.
Yes, exactly. We have a refiner here
Mm-hmm.
in the US, and I just had like a meeting with a potential customer, and he says, that we have a lot of trips, and every time we come back, our catalyst operating temperature to make the same product is exactly the same. And we have three other hydrotreaters that are trickle beds. Every time we have a failure, the starting temperature is higher. So
Right.
what do you think mean about reliability? You want to make your cycle length. That's the main thing.
Sure.
And if your unit is more reliable, you make it very easily.
I guess the
Gotcha.
other question we've got about reliability before has been regarding the recycle pump,
Mm-hmm.
and how reliable that pump is. So we typically see the mean time between failure for those pumps around 4 years. So again, we definitely feel like you can meet cycle length with the single pump in operation, and that's not going to be a reason to bring the unit down either.
Right. Right. Cool. Here's another question. Is there an MHC mode benefit for either VGO or diesel cracking to utilize isotherming benefits? So an MHC mode for VGO or diesel cracking to utilize isotherming benefits.
Doug, you're getting quite the acronym this
I know.
morning.
And some of these I'm going, I have no idea what
I
this
understood
acronym
you
is.
perfectly, Doug.
Now I do know what ULSD is,
So
but
MHC is mild hydrocracking, which C&D actually has quite a
okay.
bit of familiarity with
Okay.
our units that operate in that mode. So I'll let him take that question.
Sure.
So yes, we have four VGO hydrotreaters. All VGO hydrotreaters do some level of cracking. When the US hydrotreaters, one of them came on, we got about 10% diesel. And the other units we have, they do some mild hydrocracking. They were designed for mild hydrocracking, but subsequently the refinery is using it just as a hydrotreater, so they don't have hydrocracking catalyst in it. But again, I think that it's something that our technology is very capable of doing. There has been a lot of interest in that, particularly because refiners want to improve their bottoms upgrading, and this is one way to do it. Um, I think, in terms of diesel hydrocracking, we have a limit because isotherming can handle maybe only 20 to 25% naphtha production.
Mm-hmm.
So beyond that, we can maintain single phase. So we do have a limit in terms of cracking diesel. So in Asia, there is some idea that we have too much diesel and we want to hydrocrack it and make more gasoline. And again, I think we should keep in mind that isotherming is a liquid phase process, so we can only generate so much gas and light ends. So as long as, the refiner wants to stay within those limits, we have a good solution.
Sure.
And also, we talked during the recording about isotherming does a really good job when there's high hydrogen consumption services. So mild hydrocracking is, an extremely exothermic process. So we are going to be more efficient with, heat integration, heat transfer, likely be able to produce steam or electricity from units operating in that mode, probably have a longer cycle length because we're going to manage the temperature release profile in the reactor better. And then when you get into the VGO range material and you start talking about more contaminants or higher nitrogen, with us utilizing the recycle, we dilute a lot of those, items in the feed to lower levels. Let's say a feed comes in with 1,500 ppm nitrogen in it. In trickle bed, that's what's going to be seen on the catalyst surface. Whereas in isotherming, we may have a recycle ratio of 3 or 4. So that's going to get, diluted down to maybe, let's say, 500 ppm nitrogen seen on the catalyst surface. So when you start getting into some of these more difficult applications, talking VGO range material, that's another benefit of our technology as well.
Okay. This question, if you have no other comments on that one, this question, I think we addressed a lot of this in the recorded part, but just to make sure, let me ask this one. What is the main difference between isotherming and more conventional distillates hydrotreating technologies? Competitive advantages, disadvantages, commercial experience, and whether the same technology could be applied for desulfurization of ATM residues? That's a big one.
So yeah, I do think that we touched on a lot of the advantages and disadvantages. So again,
Sure.
Capital cost, operating cost advantages, cycle length advantages, better, cycle length advantages related to better heat management, temperature profile throughout the reactor, plot space savings, ability to process, more cracked material in a bottlenecked unit. So I guess if you're listening to this podcast and you want to know specifically about advantages that we could bring to your unit or to a specific application, please feel free to reach out to Sandeep and I, and we can talk about, for your application, which of these benefits would you see? Because sometimes it's not always all of them.
Right.
For some applications, we may shine in some areas more than others. So we're happy to have those conversations. The next question was about atmospheric resid.
Yes, that was in there. Desulfurization of atmospheric resids.
I'll let Sandeep take that one.
Okay.
So there's quite a lot of different flavors of atmospheric resid. So,
but they all smell of sulfur, right?
So, if you have like a European type crude or a crude that the atmospheric resid is not very sour, doesn't have too much metals, if it could be done in a trickle bed fixed bed process economically, we could do it for cheaper. And I would say our cycle length will be longer than in the fixed bed process. If say we're competing against an H-oil type Axens technology, which is an ebulated bed process for the vacuum resid, I think they have an advantage when the feed is very difficult. But if the feed is not very difficult, I think we would be competitive.
Okay.
So again, it comes down to,
specifics.
It does depend on the crude and the specifics, but if you have an application that you're interested, we're happy to look at the feedstock. So just get in touch with myself or Sandeep.
Sure. Okay. So in a scenario where there is a spike in contaminant levels in the feed, how fast would it take to bring the product back on spec as compared to the conventional units? And what type of operational adjustments would have to be made to achieve that? That's a loaded one.
That's a good question for Sandy.
Perfect. So I always say that isotherming is very much an autopilot. Like, let's say, you have a feed and suddenly one of your hydrotreaters goes down and you want to channel the feed to our unit. What would happen? Let's just take an example of, say, you have heavy naphtha, cracked naphtha that, you need to put it somewhere, and you say, oh, just send it to the isotherming unit. Well, that cracked naphtha has a lot of olefins in it. So what will happen is that in isotherming, it will detect, because what happens is our bed level is automatically being adjusted based on the hydrogen consumption. Now, that's a little bit, complicated to explain, so I'm not going to do it in this call.
Sure.
But what happens is that as soon as that material is added to the feed and it hits our reactor, the hydrogen consumption will go down, and that will cause the bed level to rise, and the automatic control will automatically add more hydrogen and take care of that extra hydrogen demand. So it's automatic. So this is quite an amazing advantage. I think they have heavy coker gas oil. They have many hydrotreaters. They sometimes process LCO. And they say, Sandy, when we start up the unit, line up the unit, set up all the level controls, once it's set up, we don't really have to think about the unit anymore, because it's constantly adjusting to the change in feed, and it works very well, and it's very simple. If you think, as the hydrogen consumption requirement changes, the bed level will change, and then the bed level changes, it adds more hydrogen. It's pretty much a no-brainer.
So all the controls for adjustments as necessary based on what's coming in as feed are included with the isotherming unit, it sounds like.
Absolutely. That's a core of our technology.
So you don't have to do a lot of thinking about, oh, we've got more naphtha, so we're going to have to do some changes. It does it automatically for you.
Exactly. In a trickle bed unit, you'll have to inform the isotherming operator that, hey, I'm going to send some different material. Can you handle it? What kind of preparation work is required for that? Do you want to make some adjustments in your recycle gas ratio, or change the temperature?
Sure.
Well, I think, there's of course limits to how much flexibility you have with that before, because really, you're making a product, say in a Ulsd unit, 10 ppm sulfur, you have some changes will automatically adjust, but in the end, if you have to increase the temperature to meet your product spec, that's something, you learn from experience. And that's why I mentioned, the refiner experience is quite important, in that, if suddenly you say, okay, I'm going to add some resid hydrotreater feed to it, they know that they need to raise the temperature, another 5 degrees to handle that. And actually, that's one of the beauties in isotherming is, you can raise the temperature periodically, then go back to your old temperature, and you'll see almost no activity loss, because, the system is liquid full. So, your chances of, getting excess coking is very limited. So you don't have many opportunities to deactivate the catalyst.
Sure. Yeah, along the lines of deactivation as well, Sandy, don't you think that our recycle also helps out with contaminants, in the sense that if we're getting a contaminant that might, traditionally deactivate the catalyst quite a bit, we're going to dilute it down?
Yeah, remember that. I think we mentioned this during the recording, is that the temperature rise is dampened by the recycle. So, when you put in a contaminant that requires a high hydrogen consumption in a trickle bed, you might burn up that top bed until you hit quench, whereas in isotherming, our temperature rise may be a third. And remember, in a trickle bed, you're always targeting for no more than 25 degrees F temperature rise, because after that, you better quench or you're going to reduce your cycle life.
Gotcha. All right. So is the technology applicable to treat atmospheric residue, which we sort of addressed a moment ago, to prepare feed for RFCC? Are there any units in operation with this kind of service, and not only sulfur, metals, and CCR reduction as well? So that's another mouthful, but any takers?
Sandy?
Uh-oh.
So I just want you guys to know that, again, I'm mentioning, you have to give me more specifics of the
Right.
crude, because remember, we have units operating currently that have in the past fed deasphalted oil. Deasphalted oil is more or less a resid with really very bad asphaltenes and stuff removed by propane deasphalting. So
Okay.
so again, it really depends on the resid. Like, if you put it in, let's say it's a very severe one and your nitrogen goes up, from, 1,000 ppm to 3,000 ppm. Obviously, we have to design a unit for that. We don't have one, but in Europe, I know that they have such a unit. And the GARD reactor is much larger than the hydrotreating reactor because you can't convert many of the contaminants. For example, asphaltenes. It won't get converted. It needs to be absorbed into a GARD catalyst. Metals won't get contaminated. It needs to be absorbed. And
Right.
you don't really want a unit where your cycle length is 3 months. It has to be able to capture those contaminants in a GARD reactor. So yeah, sure, we can design it, but maybe the GARD reactor is 3 times the size of the hydrotreating reactor. And in terms of temperature rise, in terms of contaminants being very concentrated at the top, with the recycle, the contaminants are at a lower level. So the contaminants don't, all come out. If you think of it, it's like titration. It's going to come out mostly on top, and as the cycle progresses, contaminants will go down through the reactor.
Right.
But what happens is when the concentration is diluted, you won't have as much of a gradient because the concentration is lower, so they'll tend to go down into the reactor more, and so you won't get shut down as you'll still get shut down when the GARD is consumed, but you won't get shut down from, say, plugging or something like that, if you
Right.
operate it correctly,
Yeah,
or if
Sandy,
you
so
design it correctly.
the guard requirements with a feedstock like that, it's really no different between trickle-bed and isotherming. So, I mean, whatever guard requirements would be there for a trickle-bed unit, we would have, a similar requirement just based on the characteristics of those feedstocks, as you said, asphaltenes, metal content, et cetera. But then when you get into the actual, hydrotreating reactor, we do think we have an advantage there.
Okay.
I would say, if you're from this person is from a Scandinavian country, give me a call. We can work something out.
Especially Scandinavia, but in the summer, right? In the summertime in the northern hemisphere. And actually, this individual wrote another little tidbit here, and I'm assuming that the question is, can isotherming take CCR from 14 weight percent to less than 5 weight percent? Metals 100 weight ppm down to less than 20 weight ppm, and sulfur reduction doesn't matter apparently too much for this individual. But if there's a question, I guess it would be, can isotherming handle this kind of feed and do these kind of properties as well?
So we don't have a commercial unit to do this, but of course, in our VGO hydrotreaters, we do CCR is one of those very difficult items, and it can't be converted. It has to be absorbed.
Right.
At least from an economic point, if you think of the pressure requirement to convert asphaltene, it's very high pressure. So really, most of our VGO hydrotreaters, the asphaltene content is quite low, maybe 1% or less. So when you go to 100 lot, and so, again, does it make economic sense? I think, what we always want to see is, we don't want to develop a technology that doesn't make economic sense.
Well, hey, that seems to wrap up our questions. Our next topic will be don't lose your competitive edge, tighten control on acid consumption in your Stratco alkylation unit using advanced process control. It's a huge title. I don't think it'd fit on the screen in a movie theater, but we're going to have Dave Derricott and Kate Smith as our speakers for this topic next month. And I hope you have an opportunity to join us. If you haven't registered for next month's podcast yet, please do so as soon as possible on refiningpitstop.com. And remember, we'll be broadcasting all of these podcasts the first Wednesday of every month. And this recording of this live session today will be out there within the next week. So until next month, keep it running down the road, and we'll see you again when you come in for the next pit stop.
Thanks, Doug.
Thanks,
Doug. Bye. Thank you, everyone.